Okay, we got 20 minutes for class. And then we got a video.
20 minutes.
Where'd you go?
So we're gonna go for
Don't knock that over. Because you're always wandering around.
Wait, can you please play
And don't forget, we got a quiz on Friday.
what song was it?
Thanks, you.
Benny and the Jets?
You're gonna need your graphic calculator.
You look kind of peppy.
Plus, you gotta get the lecture. The lecture is like the most important thing today. Because we have to be able to. Number 4, is that the only question?
Oh, wait.
Wait, what about, okay, let me ask the question. These are the ones that you're gonna see on the quiz. What about, everybody got number 3 and 4?
Yup.
Yes.
Even Daisuke.
Even Osumi
I couldn't get
and
that.
Kojima?
I'm like,
Couldn't
doing
get
homework.
number 2.
Well, that's why shouldn't we do number 3?
No.
Why couldn't we do
Yes,
number
I'm gonna do number 3 for Osumi and Kojima. Number 3.
2? Well, yeah, I can do it.
I found the pattern.
Can you do 2A?
2A, are you joking? That's a joke.
Okay, I'll tell me tomorrow morning.
Yeah, I did my homework.
Okay, it says find the 1,000th term. So what you need to do is you need to write out a few terms so that until you can see a pattern there, right? Okay, so the first term is 3, the second term is 5. Now this recursion formula, to get any term in the sequence, you take the previous term and then you subtract the one before that. So to get the third term, it's going to be 5 minus 3.
2.
To get this term, 2 minus 5.
-2.
And then to get this term,
-5.
this minus that.
-3. 3.
I don't see a pattern here, Mr. Park, but I keep writing.
-2.
This minus that.
2.
That
3.
minus that.
5.
And that minus that.
Oh,
Oh!
I see a pattern, Mr. Park.
Oh, Mr. Park, the thing was just started. So this sequence repeats every 6. Did you guys figure out? This is an SAT problem, by the way.
Yeah.
Yeah, they have problems. Except they don't give this, they say it in words, they say every term is like the previous term minus the term before that.
Or 1/7.
Or something like that. So, if we know this thing repeats every 6, then what? How do I find the 1,000 term?
Divide by 6
Yeah,
and
so
get the remainder.
1,000 divided by 6. 6 goes into that one time, 4 remainder. 6, 4 remainder. 6, remainder 4. So if the remainder is 4, you go 1, 2, 3, 4. And the answer is -3.
Cat.
That's 4 in French, I believe.
Cat is French. Quattro. What is that?
Q-U-A-T-R-E, I think. It's spelled out. I don't
Quat.
know.
Quat.
Cat.
Quat.
Okay, can we just do this? We're wasting time. Osumi, number 2A. Write out the first few terms. Okay, Osumi, tell me what the first few terms are.
I don't know.
2,
2, 7,
12.
17.
Isn't that arithmetic?
Oh, yeah.
And if it's arithmetic, you have a formula.
Okay.
Okay, now what about number 4? Do we need to do number 4?
No.
I think we do. I think we do.
It's on the board.
I got it.
Oh, it's on the board.
I did my homework.
A1, A-N. Why are you announcing that?
So proud.
What? You want to be congratulated on things you're supposed to do?
No, like all
Okay,
the
now
time.
we already know the first term is 1. Now, to get the second term, now see, what might be confusing for some of you? To get any term in the sequence, you take the previous term and add that. Yeah, but Mr. Park, what do I plug in for n? Well, you're trying to find the second term, which is a sub 2, right? So what number do I plug in for n? 2. So if I plug in 2 for n here, then you plug it in there, you're going to get a1, which is the previous term, plus, plug in 2 here, that's going to be 12 minus 6 plus 1, which is 7. So to get the second term, you got to add 7 to the first term, which is 8. To get the third term, you plug in 3 for n. This is a function. A sequence is a function. So you mean a sub 2 plus, and then you plug in 3 for n. What is that? 27 minus 9 is 18 plus 1 is 19. So the third term is a sub 2 plus 19. 27. I'm starting to see a pattern, Mr. Park.
I don't see.
Q.
There's no Q.
Oh, yeah.
Well, it looks like a Q. You think you can tell a pattern from just 3 numbers?
No.
That's right. So I would go one more just to make sure. A4 equals A3 plus So if I plug in 4 for n, what is that? 48 minus 12, 36 plus 1 is 37. So add 37 to the third term and you get
45. No.
what? 64. And then now we can see the explicit formula is n cubed. So therefore, what term are we trying to find? The 100 term, plug in 100, 100 cubed is 10 to the 6, 1 million. $1 million!
What?
And then I will do one of them, number 7. Very good. Everybody can do number 6. So one of these word problems is going to be on tomorrow's quiz now. You're going to have to use your calculator. Number 7. Newton takes 100 milligrams of a cold medicine. So the first term is 100. At the end of 4 hours, 40. Now the other class couldn't understand this. 40% of the medicine dissipates, which means how much is left?
0.6.
Yeah, so 0.6. 60% remains in his body. 40% is gone. You get it?
Yes.
Okay. And then on top of that, he tanks another 100 milligrams.
Does
Yeah.
he die?
Well, that's it. That's the question. So if you keep doing this, what is the medicine in your body just going to increase without bound, or is it going to level off at a certain number?
Oh, it's gonna level off.
I don't know. That's what we're trying to find. So if he keeps ingesting the cold medicine in this manner, what happens? That's the question.
It stops.
So you punch this in on your calculator. You guys should practice this, right? So the TI people, what do you do? N min is 1. U of n is equal to 0.6 u of n minus 1 plus 100, and u of n min gotta equal 100, right? You gotta tell the calculator what the first term is. Prism people, a sub n plus 1 is equal to 0.6 a sub n plus 100, and then you gotta tell it a dot equals 100, right? You have to tell the first term. And then you just keep scrolling down the table, and you're gonna see that, hey, the medicine is not increasing without bound. It's getting closer and closer to a certain number. 250 levels off, so yeah, you're not gonna overdose. But unless, well, you could, but that's why, you know, when you take cold medicines, you're supposed to take it only every 4 hours, right?
Really?
If you read the directions. If you take it like every hour, then you're gonna run into trouble. You guys ever took NyQuil? What's that? Yeah, you don't want to take that one too often. Plus, it's gonna make you fall asleep anyway.
Wait, if you drink wine with the medicine,
Fujimoto, having a problem?
what happens? Everyone
Yeah.
else has the tea.
Wait, you didn't do A naught. Go back to the things. Set.
If you drink wine,
There, A naught. Okay, start 0, and the end. The end should be at least 100. Because you don't want to just look at 5 terms, right? Otani, coming up. Sure. Okay,
I got it.
very good. Okay, we have 12 minutes for a lecture.
Is it enough?
Or 15, I guess we can go. Okay, so in this problem that we just did, that's kind of like today's lesson. See how the terms of the sequence keep getting closer and closer to 250? We say that the limit of that sequence is 250. That means as you write out the terms, the numbers get closer and closer to 250. The limit of that sequence is 250. So tonight's homework is I'm going to give you a sequence. You have to tell me what the limit is. In other words, as n gets larger and larger and larger, as n approaches infinity, what are the terms of the sequence getting closer and closer?
calculator or
No calculator at all.
oh, Kojima.
Okay, let's start off with a really easy one. A sub n equal 1 over n. Now, what you should do is at the beginning, when you're first learning, is write out like the first 4, 5, 6 terms just to get a feel of it. So if I plug in 1, 2, 3, 4, 5, what do you get?
1,
1, 1/2, 1/3, 1/4, 1/5, dot dot dot.
0.
Now it looks like the numbers are getting closer and closer to 0, but how do you know it's 0? How do you know it's not like 0.1 or negative 0.1? How do you know it's 0? Yeah, 0 is the correct answer, but how do you know it's 0?
Because 1 over infinity.
Because what?
1 over infinity.
Infinity is not a number. I keep telling you guys that. You cannot treat infinity like a million. Infinity is a concept of going on, getting larger and larger without bound. It is not a number. You cannot treat it like a number either. Then what's infinity plus infinity?
2 infinities.
No.
Infinity square.
Oh, I know. The graph. The
Oh,
asymptote.
What asymptote?
Zero. Asymptote is 0.
What asymptote?
Horizontal.
Okay, very good. See, now you guys are coming up with something for our change. Because remember, if you were to graph y equal 1 over x, how do I know the horizontal asymptote is y equals 0? We learned this.
1 over 0 does not.
When you have a rational function, if the degree of the bottom is bigger than the top, the horizontal asymptote is y equals 0, which means the graph goes like this. Now, of course, this is the graph of y equal 1 over x, but if you want to graph y equal 1 over n, remember the domain is the positive integers. Except it's the same thing except we have dots instead of a continuous function like that. Yeah? But you can see, yeah, it's getting closer and closer to 0. So, oh, Mr. Park, I need to know my rules for horizontal asymptotes. Yes!
No.
You gotta know all your graphs, people, in this chapter. That's what's gonna hold you back. Okay, so let's kick it up a notch. What did you have? 2n plus 3 over 5n plus 7. Without drawing this graph, tell me what the limit of the sequence is.
Negative 5 over 7 over 5.
No, it's 2/5.
What?
Because if you were to draw this graph, what would the horizontal asymptote be? If the degree of the top and the bottom are the same, you look at the coefficients, which is 2/5. So that means if you were to draw this graph, x and y equals 2/5 is the horizontal asymptote. So when the graph is going out to the right, it's getting closer and closer to that.
Why is it 2/5?
Because if the degree of the top and the bottom are the same, you look at the coefficients. We did this in the second quarter. It's like you guys never seen this before. Oh,
What?
Bifano?
No.
No, this is how you're looking. That was the Paulo face. See? Okay, you guys think you're good. Okay, and then this is how I kick it up a notch. Sine inverse. N plus 1 over 2n plus 3.
Oh, that's right.
Okay, now, forget the sine inverse, wasn't scary. Just, no.
Oh.
Well, I'll tell you what, if you could draw every single graph on the homework, then the problem is easy, but I'll tell you right now, you're not going to be able to draw most of those.
What's sine?
Some of you can't even graph the basic one.
Is that arc sine?
Okay, forget that. Yes, that's the same as arc sine. Okay, what's the limit of the thing in the parentheses? We just talked about it. If the degree of the top and the bottom are the same, you look at the coefficients. So this gets closer to a half. That's the way we do it in mathematics. You go. So you get distracted then? I'll just ignore it. So you go on a picnic with your family like that, and a fly's around, all you can think of is the fly. Okay, that gets closer and closer to a half, so the whole thing gets closer and closer to sine inverse 1/2, which is?
Pi over 4.
No.
Oh, pi over 6.
Pi over 6 is the limit.
Also, we have to know the ranges of first sine.
You gotta know everything. That's what makes it so difficult. You gotta know your base graph. Okay, what about this? D sub n is equal to n squared over n plus 1. What happens when the degree at the top is bigger?
You divide, long division.
Oblique.
Okay, there's gonna be an oblique asymptote, but is it slope? Sloping up or sloping down?
Oh, that will be sloping. Oh,
Or just think about it. If you plug in a really huge number for n, like a billion, you get a billion squared on the top, but the bottom is only 1,000,000,001.
Why not?
Right? So that's like a really big number. So you know that. So the graph gets closer and closer to it. So if the terms of the sequence are getting bigger and bigger without bound, what do you think the limit's going to be? Infinity. It's just getting bigger and bigger without bound.
Oh.
Okay. Didn't think we were gonna take that long on just rational functions. Now, when you do your homework tonight, what you gotta do is you gotta start categorizing. When I see a rational function, I'm gonna look at the degree at the top and the bottom. When you see this kind of problem, I do this. When I see this kind of problem, I do this. So what about something like this? E sub n equal tan inverse n. See now, if you plug in the first 5, if you write out the first 5 terms, tan inverse 1, tan inverse 2, tan inverse 3, tan inverse 4, for most people that doesn't mean anything, right? See, Kojima's giving me the blank look too. So what you need to do is, lots of times, is look at the graph. What does the graph of tan inverse look like? Here, I'll draw it for you because some of you might have forgotten. So when the graph is going out to the right, the y coordinates are getting closer and closer to pi over 2, that's right. But of course, if I draw the graph for you, it's so easy. The graph got to be here, which it's not for some of you, yeah?
It is.
So Mr. Park, we got to know all our base graphs.
Yes.
Yes. Yes, all of them. All of them.
All of it. Even E?
You need e to the x.
Yeah.
Yeah? Oh my goodness. Okay, what about this? You guys think you're good? I think you guys got it right. What about sine n?
Oh.
Okay, think of this graph. Ooh. As the graph is going out to the right, is it getting closer and closer to something?
No.
No, so
Then it does not exist.
exactly, mean girls. The limit does not exist because it's not getting closer and closer to something, and it is not getting larger and larger without bounds. So we say the limit does not exist because all it's doing is oscillating. That's why.
Oh, must. Wait, is that?
Yeah, go ahead. Go home and watch Mean
Oh, I
Girls
mean, like-
just for that.
Don't you have to
I
look on
just-
your computer?
yeah, I have
She
to-
says on the equation, yeah?
Yeah.
Yeah,
She
it's
says
like
that.
the Chinaman's way. Like, look at the.
Okay, we got a few minutes left. You guys want to just read the examples on your own?
No.
I didn't think so. Okay, so let's do another one. What about this? A sub n equal 1/2 to the n. Okay, before we even talk about what the limit is, what kind of sequence is this?
Exponential.
Yeah, but it is exponential, but we call it geometric. Exponential and geometric, same thing.
Yep.
Okay, let's write out the first few terms. Plug in 1, 2, 3, 4. 1/2, 1/4, 1/8, 1/16, 1/32, dot dot dot. You can clearly see the limit is 0. Okay, but I want to generalize something. When you have a geometric sequence is always going to be you have a number to the nth power. See, like 1/2 to the nth power.
Oh, and is next.
So if you know what the common ratio is, then you can figure out what the limit's going to be. So, just to save time here, if the common ratio is between -1 and 1, what do you think the limit's going to be? Just like this problem. It's going to be 0. So like what if you saw this? E sub n equal -1/3 to the n.
Zero.
It's 0. Yo, Mr. Park, when you write out the terms, the first term is -1/3, then go be +1/9, and then go be -1/27, and then +1/81. The thing is going negative, positive. Yes, it's oscillating, but the terms of the sequence are still getting closer and closer to 0.
Oh.
It's oscillating like this. Ooh.
Oh.
Yeah. So even though it's oscillating, it's still getting closer to 0. You get it?
Yeah.
Okay, now what would happen if the common ratio is bigger than 1? Like for example,
Infinity.
2 to the n. Infinity is not a number. Oh, you're giving me the answer.
Yeah.
I thought you were naming a number bigger than 1. Okay, write out the first 4 terms. 2, 2 to the second, 4, 8, 16. Hey, these numbers are getting bigger without bound. Infinity is the limit.
Oh, Eric. Ahead of the game.
What if the common ratio is less than -1? Like what if we had something like this, -3 to the n?
Negative infinity.
So that's gonna, be careful. -3, plug in 2, +9, -27, +81.
Oh.
The limit does not exist. Because it is not getting bigger without bound, because some of the terms are negative and some of them are positive. It's oscillating like this. So in this case, the limit does not, I'm just gonna put does not exist.
Done.
You cannot do that though. You gotta write does not exist unless you have a legend on your paper saying DNE means does not exist. Okay, we got time for one more example.
Yes. Yay.
What would happen if both the top and the bottom both go to infinity like this? A sub n equal n squared over 2 to the n. See, like by itself, if you plug in a huge, super huge number for n, you're gonna get a super huge number, right? So that goes to infinity. And the bottom by itself goes to infinity. So both the top and the bottom are both going to infinity. Which one is going to infinity faster though?
Both at the same time.
Just to save time? No, it's not. Because some functions go to infinity faster than others. So when that happens, we use n to the n tuple. Yeah, okay. This is just a mnemonic to help you categorize the function. N to the n. N to the n is the fastest function we know that goes to infinity. Like if you were to graph it, it just explodes to infinity very quickly. F stands for factorial, like n factorial. So if you were to graph that, it goes to infinity fast, very quickly, but not as quick as n to the n. E stands for exponential functions. That would be like e to the x, 2 to the x, 5 to the x. Those go to infinity very quickly, but not as quick as these two. What do you think P stands for?
Linear.
Polynomial. What?
Oh.
It's a P! Polynomial, like x squared, x cubed, x to the 4. The graphs look like that. They go into infinity kind of quickly, but not as quick as the first three.
Linear.
No, logarithmic. Linear is polynomial.
Oh, so I was right.
Polynomial is like x to a number power.
Oh, nice.
And the last one is logarithmic. Like, what does the graph of natural log x look like? It's like that, right? It goes to infinity, but very, very turtle-like, very slowly. See how these ones go? So this n to the n tuple tells you which functions go to infinity faster. Okay, we have 1 minute left. So, how do I classify this?
N to the N.
That's polynomial. I don't see n to the n, that's n squared.
Oh, yeah.
This is
P over n to the
polynomial,
n.
that is
N to the N.
exponential. N to the n is n to the n.
Oh.
Oh, so both
That's
have
2
be
to
N.
the n. That's not n to the n.
Both has to be N. Okay.
Yeah, but both have to be n. Okay, so this is polynomial, that's exponential. Which one is going to infinity faster?
E.
Uh,
E.
Exponential. So if the bottom is growing much faster than the top, what do you think the limit is?
0.
0, that's right. Because when you plug in a really huge number for n, this one is going to be way bigger than that.
Oh, nice.
Isn't that common sense? Not really.
That's in my
Okay, last one and we're done. B sub n equal n to the n over n factorial.
Oh.
I got this.
Okay, well, they both go to infinity. Okay, that's n to the n.
Okay, that's fast.
That's factorial, that's a
Kinda
dog.
slow.
Which one is going faster?
Well, N to the N.
Yeah, the top, so if the top is growing faster than the bottom, what do you think the limit is?
Infinity.
Infinity! See how you got all these different things, so what you gotta do is you gotta categorize.
N to the N.
Is there no negative infinity?
Yeah, there is a negative infinity. Like, for example, what about this? A sub n equal negative n squared. If you were to draw the graph, that's like a parabola upside down, right? So as the graph is going out to the right, what's happening with the y coordinates? They're getting really big negatives, so negative infinity would be that. Yeah, so you can have negative infinity as well.
It's not a number though.
Yeah, it's not a number, thank you.
What is that?
Okay, so this is what's gonna happen. You take all your stuff, you go outside. I gotta do a quick introduction. When you hear Benny and the Jets start playing, then you start coming in.
Yes. We take our
You write 3 numbers on the board,
2, 3, 5.
whatever you want.
1 through 10 or 1 through
43. 2,
11?
3, 5.
And when the and make sure you have your calculators ready.
Wait, we take everything?
Yeah, because there's nobody in class here.
Oh.
Oh no.